Hello, welcome to another module in this massive open online course on principles of MIMO, CDMA and OFDM wireless communication systems. And as we have seen in the previous module, what we are looking at the performance analysis for a basic wireline communication system, which we said can be modeled as an additive white Gaussian noise channel, that is y equals x plus n, where x is the transmitted symbol, y is the received symbol, the noise n is additive and white Gaussian in nature, with the following probability density function, that is f of n is 1 over square root of 2 pi sigma square e raised to minus n square by 2 sigma square, where sigma square is the variance or the noise power and this noise has a 0 mean. We are also considering BPSK modulated symbols, where 0 is mapped to the voltage level minus square root of p and 1 is mapped to the voltage level where 0 is mapped to the voltage level plus square root of p and 1 is mapped to the voltage level minus square root of p. Let us now consider the transmission of the information symbol 1. So, now let us say consider x, that is transmitted symbol x equals information symbol 1, which corresponds to the voltage level minus square root of p. So, let us say 1 corresponds to the, so let us say our transmitted symbol is 1 corresponding to the voltage level minus square root of p. At the receiver we have the received symbol y, which is equal to x plus n, which is equal to x plus n. Since x is equal to minus square root of p, in this case this is minus square root of p plus n. And as we had seen before, since we are transmitting the voltage symbol 1, correct, and therefore there will be an error if the received symbol is decoded as the information symbol 0, and that happens when the received symbol is greater than or equal to 0. So, there will be a bit error if y is, so error occurs or bit error occurs if y is greater than or equal to 0, because if y is greater than or equal to 0, it is mapped to the information symbol 0. However, we are transmitting the information symbol 1. Therefore, this corresponds to the bit error rate 0, bit error rate if y is greater than or equal to 0. And y is greater than or equal to 0, this implies naturally minus square root of p plus n is greater than or equal to 0, which basically implies that n is greater than or equal to square root of n is greater than or equal to square root of p. That is, the Gaussian noise n, the additive white Gaussian noise n is greater than or equal to square root of p. And therefore, this happens, that is probability of error, therefore, naturally probability of error equals the probability that this Gaussian noise n is greater than or equal to square root of p, and this can be obtained as the integral from square root of p to infinity of the probability density function of the noise from between the limits square root of p to infinity. So, we are looking at the probability that the noise is greater than or equal to square root of p, and we are saying that is equal to basically the integral of the probability density function of the noise f of n between the limits square root of p to infinity. Now, what I am going to do is I am going to substitute the probability density function of the noise. We know that the noise follows the Gaussian probability density function, which we had mentioned earlier. So, this is 1 over square root of 2 pi sigma square e raised to minus n square divided by 2 sigma square times dn. And now, what I am going to do is I am going to use the substitution n by sigma equals t, which means dn equals sigma dt, and therefore, this integral can be written as this is the integral, the limit becomes square root of p over sigma, infinity over sigma is infinity, 1 over square root of 2 pi, I am bringing sigma out of the square root, times sigma, e to the power of minus n square by sigma square becomes t square by 2, and dn is sigma dt, and therefore, now you have these two sigmas cancelling, and therefore, what I have net is, if I look at the probability of bit error, that is the probability of error equals the probability that this noise n is greater than the square root of p. This is equal to the integral, as we have seen before, integral square root of p over sigma to infinity 1 over square root of 2 pi e raised to minus t square over 2 times dt. And now you can easily see that this expression 1 over square root of 2 pi times e raised to minus t square over 2, this corresponds to a Gaussian distribution of a Gaussian random variable with mean 0 and variance 1, right. So, this corresponds to a Gaussian random variable, this corresponds to a Gaussian RV with mean equal to 0 and variance equal to 1, and therefore, what we are asking is what is the probability that this Gaussian random variable with mean 0 and variance 1 is greater than or equal to this threshold p over sigma square, and this is given as, basically this is given as the q function q of square root of p over sigma square, where the definition of the q function is q of v is the integral between the limit v to infinity 1 over square root of 2 pi e raised to minus t square by 2 of t square by 2 times dt, correct. So, what we are seeing is that this probability of error is, as you can see here, is integral between square root, between the limit square root of p divided by sigma to infinity 1 over square root of 2 pi times e raised to minus t square by 2 dt, and therefore, this quantity is the Gaussian random variable with mean 0 and variance 1, and hence this function is the q function, and therefore, the probability of bit error is given as q of square root of p divided by sigma square, where q of v is defined as the integral from v to infinity 1 over square root of 2 pi e raised to minus t square by 2 of dt. So, the bit error rate of the wire line communication system, that is without multipath propagation, with only additive white Gaussian noise without any fading, is given as the probability of bit error is equal to q of square root of p divided by sigma square. So, the probability, let me just write this down, probability of bit error the probability of bit error in an AWGN channel equals q probability of bit error in an AWGN channel equals q of square root of p divided by sigma square, and this is the probability of bit error for a BPSK modulated system, probability of bit error for BPSK modulated transmission, for BPSK modulated transmission with average power p. For BPSK modulated transmission of average power equals p. Further, you can also see p by sigma square equals the SNR, and therefore, this bit error rate is also q of square root of the SNR of communication. Further, you can see since P is the transmitted power, sigma square is the noise power, P by sigma square is the SNR or signal to noise power ratio of the communication system. So, we can say P by sigma square equals SNR, where SNR denotes signal to noise power ratio of the communication system. Therefore, we have an elegant expression for the bit error rate in terms of the SNR. It simply says that the bit error rate for BPSK modulated transmission over an additive white Gaussian noise channel is simply Q of square root of SNR, that is the Q function of the square root of the SNR, signal to noise power ratio of the communication system. Correct. So, let us do a couple of examples to understand this better. So, the first example, let us do a couple of examples. So, in the first example, what we want to do is we want to compute at SNR equals 10 dB. So, we want to ask the question at SNR at a signal to noise power ratio of 10 dB, what is the bit error rate? What is the BER for our AWGN communication system? For our AWGN communication system with BPSK modulation. With BPSK modulation system, and what we have seen is that at SNR equals 10 dB, which means that our 10 log 10, that is, this is the dB SNR, therefore 10 log 10 SNR equals 10 dB, which means log 10 of SNR equals 1, which means SNR equals 10 to the power of 1, which is equal to 10. So, 10 dB SNR in dB corresponds to an SNR of 10, and we know from the previous, from what we already derived, that the probability of bit error is Q of square root of SNR. Therefore, the probability of error PE equals Q of square root of SNR, which is equal to Q of square root of 10, and this is equal to, there is no closed form expression to compute the Q function. So, I have to compute it from the tables, and this value is equal to 7.82 times 10 power minus 4. So, this is the probability of bit error. What is this? This is the probability of bit error of BPSK modulated transmission over an AWGN channel at SNR of 10 dB. So, this is probability of bit error for BPSK over AWGN channel at SNR equals 10 at SNR equals 10 dB, correct. And as we have said, there is no closed form expression for this Q function, correct, and therefore, this has to be evaluated using some software or online tables that are available for this Q function, and this gives us the value of 7.82 times 10 power minus 4, which is the bit error rate. Another convenient way to evaluate this is if we are not using for looking for an accurate or the exact, to evaluate the exact value, or if we are rather looking for a convenient approximation for this Q function, then we can use the approximation, that is, we can use the approximation Q of x, which is less than or equal to half e to the power of minus half x square. So, this is a bound, that is q of x is less than or equal to half e to the power of minus half x square, e to the power of minus half x square, and this bound I can use it as a convenient approximation. We can use it as a convenient approximation for the q function. And therefore, what we will have is we will use frequently the approximation q of x is approximately equal to half e to the power of minus half x square. Therefore, our bit error rate, which is q of square root of SNR, will approximately be half e to the power of minus half square root of SNR square, which is simply SNR. So, our approximate bit error rate for BPSK modulated transmission over the AWGN channel is half e to the power of minus half SNR. So, this is our approximation of BER for BPSK over the AWGN channel, that is half e to the power of minus half SNR. So, we can use this approximation, and using this approximation we can recalculate the SNR, the bit error rate for the previous example as BER equals half e to the power of minus half times the SNR is 10, which is half e to the power of minus 5, which is equal to 3.91 into 10 power minus 4. This is the approximate bit error rate at 10 dB SNR. Approximate bit error rate at SNR equals to 10 dB, which we have, and you can see this is fairly close, that is 3.91 into 10 power minus 4 is fairly close to the exact value that we calculated, which is 7.82 into 10 power minus 4. So, this is the approximate bit error rate at SNR equals 10 dB. We can look at another example in which we are asking the alternative kind of question. We are asking it in the reverse form, that is, given a certain bit error rate, one can ask what is the minimum SNR, what is the SNR required for transmission. So, let us look at that example also, which, so another example is the following thing, which is the same question in reverse, that is, what is the SNR dB SNR in dB required for bit error rate equals 10 power minus 6, again for BPSK over AWGN. This is again for BPSK over an AWGN channel. And this SNR required can be calculated as follows. We have half e to the power of minus half SNR using our approximation is equal to 10 power minus 6, which basically implies e to the power of minus half SNR is twice into 10 power minus 6, which basically implies SNR equals minus 2 times the natural logarithm or log to the base e of twice into 10 power minus 6, which is basically the value is 26.24. So, the SNR required is 26.24. The SNR in dB is 10 log to the base 10 of this value. Therefore, the SNR in dB is 10 log to the base 10 of 26.24, which is 14.19 dB. So, the SNR in dB, so the SNR in dB equals 14.19 dB. This is the approximate, this is the SNR required for BPSK transmission over the AWGN channel in order to achieve a bit error rate of 10 power minus 6. So, our question, remember our question was what is the SNR in dB required to achieve bit error rate of 10 power minus 6 for BPSK transmission over the AWGN communication channel, and our answer is that this SNR is approximately equal to 14.19 dB. So, these are the two examples which illustrate how do we analyze the performance of a communication system, a digital communication system with digital modulation, that is BPSK, binary phase shift keying, over a channel with no fading, that is simply additive white Gaussian noise and no fading, that is this corresponds to a wireline channel where there is no multipath propagation, there is a single wire path between the transmitter and the receiver, and we have seen that the bit error rate for this simplistic system is given by the elegant expression Q function or Q of square root of SNR, and we have seen some examples where we have calculated the bit error rate for a given SNR, and we also calculated the SNR required for a given bit error rate. So, this completes the analysis for the performance of a AWGN channel communication system. Next, we are going to look at the performance analysis for a wireless communication system with fading between the transmitter receiver, and that is going to show us some interesting results and some interesting insights into the performance of these wireless communication systems. So, we will end this module here. Thank you very much.